Hello and welcome. Tonight, we'll be exploring one of the most astonishing discoveries ever made in astronomy, the mysterious objects known as quasars. They shine with a brilliance so extraordinary that a single one can outshine an entire galaxy filled with hundreds of billions of stars. Yet despite their incredible power, they remained completely invisible for most of human history, quietly hiding in the darkness beyond our eyes. It is a story filled with curiosity rather than danger, with patient observation rather than sudden revelation. Like so many great discoveries in science, it began not with certainty, but with a question that seemed impossible to answer. So, find a comfortable place to rest, allow your thoughts to slow with each gentle breath, and let us begin our journey into one of the most remarkable mysteries the universe has ever offered. For thousands of years, the night sky appeared calm and familiar. People looked upward and saw bright stars scattered across the darkness, the soft glow of the Milky Way stretching from one horizon to the other, and a handful of wandering planets slowly moving among the constellations. It seemed like a peaceful, orderly universe. Even as telescopes improved over the centuries, much of that feeling remained. Astronomers discovered beautiful nebulae where new stars were born. They learned that our own Milky Way was only one galaxy among countless others. Every new observation made the universe seem larger, but also a little more understandable. By the middle of the 20th century, many scientists felt that they were slowly assembling the great puzzle of the cosmos. There were stars, galaxies, clusters of galaxies, and the vast dark spaces between them. The picture was becoming clearer with every passing decade. Then, almost by accident, humanity learned that the universe had been speaking in a language no one had ever listened to before. The story began not with visible light, but with radio waves. Unlike the light our eyes can see, radio waves are much longer and completely invisible to us. Yet they travel through space just as faithfully, carrying information across unimaginable distances. Long before astronomers learned to use them, these gentle waves had already been crossing the universe for millions, sometimes billions, of years. In the 1930s, an engineer named Karl Jansky was studying sources of radio interference that affected communication systems on Earth. He expected to find thunderstorms, electrical equipment, or perhaps signals produced by human technology. Instead, he discovered something wonderfully unexpected. A faint radio whisper arrived each day from nearly the same direction in the sky. It did not come from Earth. It did not come from the sun. It came from deep space. Imagine sitting quietly in your home late at night. You hear the soft sound of distant music drifting through an open window. You cannot see who is playing. You cannot even tell exactly where it comes from. Yet you know that somewhere beyond the darkness, someone is there. That was how the universe first introduced itself through radio astronomy. As new radio telescopes became larger and more sensitive, astronomers began listening more carefully. They discovered familiar objects that also produced radio waves, including nearby galaxies and the remains of exploded stars. But hidden among these recognizable sources were stranger signals. Tiny points, small, faint, impossible to identify. Some appeared where no visible object could be seen at all. This created a remarkable mystery. If these radio sources were nearby, astronomers should have been able to see them with ordinary telescopes. If they were unimaginably distant, then they had to be producing astonishing amounts of energy, far more than anyone believed possible. Neither explanation seemed satisfying. Many scientists wondered whether their instruments were somehow making mistakes. Others suspected that entirely new kinds of celestial objects might exist. The debate continued for years until a fortunate opportunity arrived. One particular radio source, known simply as 3C273, happened to pass behind the Moon from Earth's point of view. As the Moon briefly blocked its radio signal, astronomers could measure its position with extraordinary precision. It was like hearing a distant bell disappear behind a hill, allowing you to pinpoint exactly where it had been ringing. With that improved position, astronomer Martin Schmidt examined a faint point of light that seemed to match the radio source. At first, nothing looked especially unusual. The object appeared almost star-like, but when Schmidt carefully separated its light into a spectrum, something remarkable appeared. Every chemical element leaves its own unique pattern within light, almost like a fingerprint. Hydrogen has its own pattern, helium has another. By reading these delicate fingerprints, astronomers can learn what distant objects are made of. The fingerprints inside this mysterious object were all present, but they were shifted. Every line had moved gently toward the red end of the spectrum. The explanation was breathtaking. The object was not nearby at all. It was billions of light years away. Its light had spent billions of years travelling across an expanding universe before finally reaching Earth. As space itself slowly stretched during that immense journey, the light stretched with it, becoming slightly redder along the way. Suddenly, everything changed. If this tiny point of light truly lived so far away, then it had to be unimaginably luminous. It was producing more energy than entire galaxies. No ordinary star could possibly do such a thing. Astronomers gave these mysterious objects a rather long name, quasi-stellar radio sources, because they looked almost like stars while producing powerful radio signals. Fortunately, scientists soon shortened the name to something much simpler, quasar. The word was easier to say, much easier to remember. Yet the mystery itself had only grown deeper. Naming something does not explain it. If anything, the new name only sharpened the question. What kind of object could shine brighter than hundreds of billions of stars while occupying a region smaller than our own solar system? Some astronomers struggled to believe the measurements. The idea seemed almost unreasonable. Others slowly accepted that nature was under no obligation to remain within the limits of human imagination. The universe, it seemed, was capable of building engines far more powerful than anything people had ever dreamed. And somewhere in the immense darkness, these silent beacons had been shining for millions of years, patiently waiting for a young civilization on a small blue world to notice their faint whispers carried upon invisible waves. The first mystery had been solved. A new one had only just begun. When astronomers finally accepted that quasars truly existed, they were left with an even greater mystery than before. The astonishing brightness of these distant objects was only the beginning. Their true importance came from something far more subtle. Every quasar was also a messenger from another age. At first, this idea may sound almost poetic, but it is one of the most beautiful realities in astronomy. The universe is so unimaginably vast that light itself needs time to travel across it. Even though light moves faster than anything else we know, it still cannot cross billions of light years in an instant. Instead, it travels patiently, year after year, century after century, million after million of years. Imagine opening an old family album filled with photographs taken decades before you were born. Every picture captures a moment that no longer exists. The smiling children have become grandparents. Tiny trees have grown into forests. Entire neighbourhoods have changed beyond recognition. Astronomy works in much the same way. Every time you look deeper into space, you are also looking further into the past. The moon appears as it was a little more than 1 second ago. The sun appears as it was about 8 minutes ago. Nearby stars show us scenes from years in the past. The most distant galaxies reveal a universe that existed billions of years before our own planet was even formed. Quasars take this remarkable idea to its extreme. Some of their light began its journey long before the Earth existed. By the time those ancient photons finally arrived, continents had drifted, mountains had risen and eroded away, countless species had appeared and disappeared, and humanity had only just begun asking questions about the stars. In this sense, Every quasar is far more than a brilliant object. It is a window, a time capsule, a letter mailed from the distant past. This simple realization transformed quasars from mysterious curiosities into some of the most valuable scientific tools ever discovered. Astronomers soon noticed another intriguing pattern. The farther they looked into the universe, the more quasars they found. Nearby galaxies were usually calm and quiet. Their centres showed little activity, but galaxies billions of light years away often contained brilliant active cores that easily outshone all the stars surrounding them. This was not a coincidence. It revealed that the universe itself had changed over time. Long ago, galaxies lived much closer together than they do today. Space was smaller, and encounters between galaxies happened much more frequently. When two galaxies drifted close enough, gravity gently pulled them together in a slow cosmic dance, lasting hundreds of millions of years. These mergers were not violent explosions, but graceful encounters on unimaginable scales. Clouds of gas drifted inward. Dust slowly spiraled toward the galactic centre. Fresh material gathered around the invisible giant hidden there. The sleeping engine awakened. A quasar was born. As the universe expanded and galaxies gradually spread farther apart, these encounters became less common. Without a steady supply of new gas flowing toward their centres, many of those brilliant engines slowly quieted. The universe did not stop making black holes, it simply became less generous in feeding them. But perhaps the greatest gift offered by quasars is not their own light. It is everything that happens to that light along its journey. Imagine driving along a country road just before sunrise. Thick layers of mist drift across the fields. Your headlights shine through them, revealing one delicate layer after another. Although the fog itself is difficult to see, the light passing through it tells you that it is there. The universe contains something surprisingly similar. Between galaxies lies an enormous amount of extremely thin hydrogen gas. It is so spread out that it would be almost impossible to detect directly. Yet when the brilliant light from a distant quasar passes through these invisible clouds, each cloud leaves behind an almost imperceptible mark upon the light. Rather than thinking of this as complicated physics, imagine placing a clean sheet of paper beneath hundreds of tiny leaves falling from a tree. Each leaf leaves behind a faint impression. One mark alone tells you very little. Thousands of marks together begin revealing the shape of the entire forest. Astronomers call this collection of delicate fingerprints the Lyman Alpha Forest. The name may sound technical, but the idea is wonderfully simple. Every invisible cloud gently stamps its own signature onto the light travelling toward us. By carefully studying those countless signatures, astronomers can reconstruct the enormous web of gas stretching between galaxies. They can estimate where matter gathered, how the universe became enriched with heavier elements, and how enormous cosmic structures slowly grew across billions of years. Quasars, in other words, illuminate things that would otherwise remain forever invisible. Their light also tells another remarkable story. Not long after the universe was born, it entered an era often called the Cosmic Dark Ages. There were no stars yet, no galaxies, only cooling gas slowly filling the expanding cosmos. Eventually the first stars ignited. The earliest galaxies followed. Their powerful light gradually transformed the surrounding hydrogen gas, changing it from a quiet, neutral state into one filled with energetic, charged particles. Astronomers describe this enormous transformation as cosmic ruinization, but you might simply imagine dawn slowly replacing a long night. Instead of darkness disappearing all at once, the first light spread gently across the universe until almost everything had awakened. Quasars help scientists study this extraordinary transition. Because their light has crossed nearly the entire observable universe, it preserves tiny clues about how quickly this great cosmic dawn unfolded. Then, just as astronomers thought they were beginning to understand the timeline, another surprise arrived. The James Webb Space Telescope began discovering quasars that already existed when the universe was astonishingly young. Some appeared less than 700 million years after the Big Bang, a period when the cosmos was still in its earliest childhood. These ancient objects were already enormous, already brilliant, already powered by black holes so massive that modern theories struggle to explain how they grew so quickly. Rather than solving the mystery of quasars, every new discovery seemed to deepen it. Their light had carried answers across billions of years. It had also delivered entirely new questions. Somewhere inside those brilliant beacons, hidden beneath unimaginable gravity and extraordinary energy, lay one of the greatest engines nature has ever constructed. Understanding that engine would require us to leave the vast spaces between galaxies behind and gently approach the quiet heart of one much closer to home, where an ancient giant has been waiting patiently at the centre of our own Milky Way. By now, the universe has begun to feel much larger than it did at the beginning of our journey. We have travelled billions of light years across space, watched ancient light cross unimaginable distances, and followed mysterious beacons back toward the earliest chapters of cosmic history. Yet sometimes the most remarkable discoveries are not waiting at the edge of the observable universe. Sometimes they're quietly hiding much closer to home. About 25,000 light-years from Earth, buried deep within the crowded centre of the Milky Way, rests an object that cannot be seen directly with ordinary eyes. It emits no steady visible light of its own. It does not sparkle like a star or glow like a nebula. For many years, astronomers knew something unusual was there without understanding exactly what it was. The region became known as Sagittarius A Star, a name that sounds almost ordinary for something so extraordinary. If you could somehow travel toward the centre of our galaxy, the peaceful neighbourhood surrounding our sun would slowly give way to an increasingly crowded environment. The distances between stars would shrink. Giant clouds of gas would drift overhead. Ancient stars would gather in enormous numbers, all moving through a region far busier than our quiet corner of the Milky Way. Imagine standing beside a calm country road at night. Only an occasional car passes. Now imagine walking into the centre of a great city during the busiest hour of the day. Lights surround you. Movement comes from every direction. Everything feels compressed together. The centre of our galaxy is something like that bustling city. Thousands upon thousands of stars crowd together into a relatively small region of space, each following its own graceful orbit under the influence of gravity. For decades, astronomers carefully watched those stars. One in particular attracted their attention. It completed its orbit with astonishing speed, sweeping around an invisible point before racing away again. Others followed similar paths, each behaving as though they were circling something incredibly massive that simply refused to reveal itself. It was a little like watching autumn leaves circle around the mouth of a hidden drain beneath dark water. You may never see the opening itself, but the motion of the leaves tells you exactly where it must be. The stars near Sagittarius A Star were doing the same thing. Their paths became nature's clues. By measuring their motion year after year, astronomers could calculate the mass of whatever occupied the centre. The answer was breathtaking. Hidden within a region smaller than our solar system was an object containing the mass of roughly 4 million suns. Nothing made of ordinary matter could remain so compact. Little by little, the evidence became impossible to ignore. The invisible giant at the centre of our galaxy was a supermassive black hole. Unlike the black holes created by collapsing stars, which usually contain only a handful of stellar masses, this one had grown into something vastly larger over cosmic time. It sat quietly at the centre of the Milky Way, shaping the motions of countless surrounding stars through gravity alone. But knowing it existed was only the beginning. Scientists naturally wanted to see it. That wish sounded almost impossible. After all, black holes do not shine. They trap light rather than producing it. Trying to photograph one might seem as hopeless as trying to photograph a shadow, in complete darkness. Yet nature offered a small advantage. Although the black hole itself remains invisible, the material surrounding it becomes incredibly hot. Gas and dust swirling around the invisible boundary glow brightly before disappearing forever. Capturing that faint glow required one of the most ambitious scientific collaborations ever attempted. Instead of building a single enormous telescope, astronomers connected radio observatories spread across the Earth. Working together with astonishing precision, these instruments effectively became one giant telescope, nearly as large as our planet. Years of careful observation and equally patient analysis finally produced an image unlike anything humanity had seen before. It was not a sharp photograph in the everyday sense. Instead, it revealed a soft ring of glowing material surrounding a dark centre. That dark region became known as the shadow of the black hole. The shadow is not the black hole itself, rather it is the area where gravity bends and captures so much light that a dark silhouette naturally appears against the glowing gas behind it. Imagine placing a perfectly black marble in front of a bright lantern while looking through gently flowing water. The light bends, shimmers, and wraps around the object in unusual ways. The darkness appears larger than the marble itself because the water redirects the light before it reaches your eyes. Gravity near a black hole performs a similar trick, although on a scale almost impossible to imagine. Space itself bends. Light follows those curves. The shadow emerges naturally from that distorted geometry. Even after obtaining this remarkable image, Sagittarius A Star appeared surprisingly calm. Compared with the brilliant quasars we encountered earlier, our galaxy's central black hole seemed almost sleepy. Only a modest amount of gas drifted toward it. Only faint bursts of radiation escaped its surroundings. The giant appeared to be resting, but appearances can be deceptive. Every so often, a wandering star ventures a little too close. Gravity grows dramatically stronger with every step toward the black hole. The side of the star nearest the centre feels a much greater pull than the far side. Eventually, the difference becomes overwhelming. The star begins to stretch, then it tears apart. Its glowing gas spirals inward, wrapping around the black hole like ribbons caught in a whirlpool. Astronomers call these dramatic events tidal disruption events, but you can simply imagine an ocean wave becoming so powerful that it slowly pulls apart an elaborate sand sculpture grain by grain. The black hole does not rush, it simply waits. Gravity does the rest. Even more surprising, our quiet galaxy carries evidence that this peaceful state has not always existed. In the year 2010, astronomers studying high-energy radiation discovered two enormous glowing structures extending above and below the centre of the Milky Way. Each stretched for roughly 50,000 light-years. Together they formed what are now known as the Fermi bubbles. These gigantic structures are invisible in ordinary light, yet they preserve the memory of an ancient outburst that occurred millions of years ago. Perhaps a giant cloud of gas drifted inward. Perhaps a dense cluster of stars wandered too close. Whatever the cause, Sagittarius A Star appears to have experienced a period of much greater activity than we witness today. It may never have rivaled the brightest quasars scattered across the distant universe, but it was certainly far from silent. Our galaxy, it seems, has known both peaceful evenings and stormy seasons. Today we happen to live during one of its quieter chapters. Yet a gentle question still lingers. If our own black hole can awaken after long periods of rest, what transforms the centres of distant galaxies into engines so brilliant that they outshine hundreds of billions of stars? The answer lies not within the black hole alone, but in the remarkable dance of gas, dust, gravity, and light that surrounds it. Not every galaxy shines with the breathtaking brilliance of a quasar. Most, like our own Milky Way today, appear calm. Their stars quietly follow familiar paths. Clouds of gas drift gently between them, and the giant black hole at the centre waits almost unnoticed. But every so often, a galaxy enters a very different chapter of its life. Fresh gas arrives. dust slowly gathers. Gravity begins pulling everything inward. A quiet centre awakens. Astronomers call this remarkable stage an active galactic nucleus, often shortened to AGN. Although the name sounds technical, the idea itself is wonderfully simple. It is simply the bright, energetic heart of a galaxy, where an enormous black hole is actively feeding. To understand how such incredible power is produced, let us imagine moving slowly toward the centre of one of these active galaxies. From a great distance, everything seems peaceful. Billions of stars form graceful spiral arms that stretch across hundreds of thousands of light years. Nothing immediately suggests that one tiny region near the centre will completely dominate the energy output of the entire galaxy. As we continue inward, the surroundings gradually change. The stars become more crowded. Clouds of gas become thicker. The air, if space had air, would almost seem hazy. Astronomers have discovered that many active galaxies are surrounded by an enormous ring of cold gas and dust. Rather than forming a thin circle, this material resembles a giant, thick donut wrapped around the galaxy's centre. This structure is known as the dust torus. It may sound like an unusual feature, but its role is surprisingly important. Imagine approaching a great city just before sunrise, while a layer of dense morning fog hangs over the streets. The city itself may already be awake, its lights glowing brightly beneath the mist. Yet from certain directions, the fog hides much of the activity. The dust torus behaves in much the same way. Depending on where we observe a galaxy from, this enormous ring can either reveal the brilliant centre or gently conceal it. In many cases, different kinds of active galaxies turn out to be remarkably similar objects viewed from different angles. As we pass through this vast ring of dust, gravity begins to dominate every movement. Gas no longer drifts aimlessly through space. Instead, it slowly begins falling toward the invisible giant waiting at the centre. Of course, almost nothing in nature falls perfectly straight. Just as rainwater swirling toward the drain in a sink begins circling before disappearing, the gas around a black hole also spirals inward. Each cloud carries a little sideways motion. That gentle sideways movement prevents an immediate plunge and instead creates a magnificent rotating structure. This is the accretion disk. Far from being a quiet, orderly ring, the disk is a place of constant motion. Clouds brush past one another. Gas becomes compressed. Tiny collisions occur everywhere. Friction slowly transforms motion into heat. As the temperature rises higher and higher, the entire disk begins glowing across many different forms of light. It is tempting to imagine that the black hole itself is somehow producing all this energy. In reality, the black hole remains completely dark. The brilliance comes from the journey toward it. A simple comparison may help. Imagine pushing a bicycle to the top of a long hill. You spend energy lifting it upward. Once you let go, the bicycle rolls back down. The energy you invested is gradually released as motion. Gravity works in a similar way. Matter located far from a black hole possesses enormous stored gravitational energy. As it slowly falls inward, that stored energy is converted into heat, light, and motion. Astronomers often describe this stored energy using the idea of binding energy, but there is no need to think of complicated calculations. Instead, picture a deep valley. Moving a single stone from the bottom of the valley to the hill above requires effort. Moving an entire mountain of stones would require vastly more effort. The deeper the valley, the harder the task becomes. A black hole creates the deepest gravitational valley known in the universe. When gas slowly slides down that immense slope, astonishing amounts of energy are released along the way. Remarkably, this process is even more efficient than the nuclear reactions inside ordinary stars. Our own sun shines because tiny particles deep within its core slowly combine, releasing energy over billions of years. Near a supermassive black hole, Simply falling inward can release even more usable energy than those powerful reactions. Nature has found another way of turning gravity into light, yet this extraordinary engine possesses something equally remarkable. It knows how to regulate itself. Imagine placing a kettle over a fire. As the water grows hotter, steam begins escaping through the spout. The escaping steam prevents pressure from building forever. Or think of a fireplace. Add too much wood at once and the flames quickly grow stronger. That stronger fire consumes fuel more rapidly until balance gradually returns. The heart of an active galaxy behaves in a surprisingly similar way. As more gas falls inward, the accretion disk becomes hotter and brighter. The brilliant light produced by the disk does not simply shine into empty space. Light itself carries a tiny amount of pressure. Normally we never notice it. Near a quasar, however, the light becomes so intense that it gently pushes back against the very gas trying to fall inward. The brighter the disk becomes, the harder it becomes for additional gas to continue falling. Some of that material is slowed, some is pushed outward. The feeding briefly eases. As the disk gradually cools, gravity once again gains the upper hand, allowing fresh material to drift inward. The cycle quietly begins again. In a sense, the giant engine almost seems to breathe. Matter falls inward. Light pushes outward. Gravity gathers. Radiation gently resists. The balance shifts back and forth over enormous spans of time. Astronomers describe the ideal balance between these opposing forces as the Eddington limit. Although the name sounds formal, the underlying idea is beautifully simple. There comes a point where the outward push from brilliant light almost equals the inward pull of gravity. Like two equally matched teams in a slow tug of war, neither side completely wins. For many years, scientists believed this balance placed a natural speed limit on how quickly black holes could grow. Yet the universe rarely enjoys following simple rules forever. Some of the earliest quasars appear to have grown much faster than this gentle balance would seem to allow. To explain these ancient giants, astronomers have proposed that under special conditions, black holes may occasionally experience periods of super-Eddington accretion. In plain language, this simply means they somehow manage to gather material even faster than expected, perhaps for relatively short periods, allowing them to gain mass with surprising speed. Exactly how this happens remains one of the great puzzles of modern astronomy. But one thing is already becoming clear: gravity alone cannot fully explain the breathtaking power of a quasar. Something else is quietly taking shape inside the glowing disk. Invisible lines of magnetic force are slowly twisting, strengthening, and preparing to launch some of the longest and most powerful structures anywhere in the universe. If gravity were the only force at work around a supermassive black hole, quasars would already be extraordinary. The slow release of gravitational energy alone would make them among the brightest objects in the universe. Yet gravity is only one musician in a much larger orchestra. Hidden within the glowing disk surrounding the black hole, another force quietly gathers strength. It cannot be seen directly. It has no colour of its own. It slips silently through space, guiding charged particles along invisible paths and shaping events across millions of light years. This quiet architect is magnetism. Most of us encounter magnetic fields almost every day without giving them much thought. A small refrigerator magnet clings gently to a metal door. A compass needle patiently points toward Earth's north. Hidden inside many bicycles, a tiny dynamo converts the spinning wheel into electricity that powers a lamp. Simple, ordinary, comfortingly familiar. Now imagine that same idea unfolding on a scale so enormous that entire galaxies become part of the machine. The gas surrounding a black hole is no longer an ordinary gas. The temperatures have become so extreme that atoms can no longer hold on to their electrons. Instead of neutral atoms quietly drifting through space, the material becomes a glowing sea of free electrons and atomic nuclei. Astronomers call this state of matter plasma. Although the word may sound unfamiliar, Plasma is actually the most common form of ordinary matter in the universe. The sun is made of plasma. Lightning briefly turns air into plasma. Even the shimmering curtains of the northern and southern lights are created by plasma interacting with Earth's magnetic field. Near a quasar, however, plasma behaves on an entirely different scale. Because the particles carry electric charge, every movement helps generate magnetic fields. As the enormous disk continues rotating around the black hole, these magnetic fields become stronger and more complicated. Imagine stirring a spoon through a cup of honey. At first, thin lines appear within the liquid. Continue stirring, and those lines begin twisting around one another. Stir faster still, and beautiful swirling patterns emerge almost on their own. Something similar happens inside the accretion disk. The plasma does not move like a perfectly smooth river. Instead, it churns. Small eddies appear. Dense clumps drift through thinner regions. Tiny disturbances grow into larger waves. Every motion gently stretches and twists the invisible magnetic field. This continual strengthening of magnetic fields is known as a magnetic dynamo. The principle is surprisingly familiar. A bicycle light powered by a dynamo becomes brighter as the wheel spins faster. Motion becomes electricity. Around a black hole, motion becomes stronger magnetic fields. Nature simply performs the same trick on a breathtaking scale. Part of the reason this process becomes so effective is that different parts of the disk move at different speeds. The material closest to the black hole races around at astonishing velocity. Material farther away travels more slowly. Imagine a group of dancers standing in several large circles around a stage. The dancers nearest the centre complete each lap very quickly. Those near the outer edge move more slowly to cover their much larger circles. Although everyone is dancing around the same stage, they do not all move together. The accretion disk behaves in much the same way. As neighbouring layers rotate at different speeds, the magnetic field becomes stretched tighter and tighter, almost like twisting a long rubber band. Eventually, those invisible strands store enormous amounts of energy. Closer still to the black hole lies a remarkable boundary. Outside this region, matter can continue circling in relatively stable paths. Inside it, the situation changes forever. There comes a final orbit where circular motion remains possible. Beyond that point, no stable path exists. Gravity becomes simply too strong. Rather than using its formal scientific name repeatedly, it may be easier to picture it as the last safe orbit. Cross that invisible boundary, and the journey changes from graceful circling to an unavoidable inward fall. Most of the gas continues quietly toward the event horizon, but not all of it. Some of the charged particles become trapped by the tangled magnetic field. Instead of falling directly inward, they begin following invisible magnetic pathways that curve above and below the spinning disk. Another extraordinary ingredient now enters the story. The black hole itself is rotating. Although nothing can escape from beyond the event horizon, the spinning black hole does something remarkable to the space surrounding it. Rather than imagining space as completely empty, imagine placing a heavy wooden spoon into a bowl of thick soup and slowly turning it. The soup nearest the spoon begins turning as well. The farther away you move, the weaker that motion becomes. A rotating black hole creates something surprisingly similar. Its tremendous gravity gently drags the surrounding fabric of space into slow rotation. This region is known as the ergosphere. Within it, space itself is no longer completely still. The twisting magnetic fields passing through this rotating region become wound tighter than ever before. One of the most successful ideas for explaining quasar jets was proposed by physicists Roger Blandford and Roman Zanayak. Their model suggests that these twisted magnetic fields can tap into part of the black hole's rotational energy. In other words, the spinning black hole does not simply consume matter, it also helps power enormous streams of energy flowing outward. Picture a tightly twisted garden hose suddenly released. water rushes forward in a powerful stream. Around a black hole, magnetic energy performs a similar role, although far more gently and continuously than any garden hose could. Charged particles are guided along these magnetic pathways and accelerated to speeds astonishingly close to the speed of light. The result is the birth of two narrow jets, extending in opposite directions above and below the black hole. For millions of years, these jets continue pouring into intergalactic space. The particles racing through them spiral around invisible magnetic field lines as they travel. That graceful spiraling motion causes them to emit a special form of light known as synchrotron radiation. Despite its technical name, the image is beautifully simple. Imagine children spinning glowing sparklers on a warm summer evening. Each spark traces elegant circles through the darkness. Electrons moving inside quasar jets create something vaguely similar, except instead of visible sparks they produce radio waves, X-rays and other forms of invisible light. The journey does not end there. Eventually, after travelling for hundreds of thousands or even millions of light years, the jets begin slowing as they encounter the thin gas between galaxies. Their energy spreads outward. Enormous glowing clouds form at each end. These vast structures, known as radio lobes, can become larger than entire galaxies. They are the final footprints left behind by particles that began their remarkable journey beside a single black hole. It is astonishing to realise that everything we have explored in this session, from invisible magnetic fields to jets stretching across intergalactic space, begins inside a region smaller than our own solar system. From something so compact comes a structure capable of influencing entire clusters of galaxies. At last, nearly every piece of the puzzle has found its place. Gravity gathers the fuel. The glowing disk releases extraordinary energy. Magnetic fields quietly grow stronger. The spinning black hole lends part of its enormous rotational power, and the universe responds by building the longest, brightest beacons it knows. Yet one mystery remains surprisingly gentle. If all of these remarkable ingredients are fundamentally the same, why do astronomers give different names to objects that appear so different across the sky? The answer, as it often does in astronomy, depends largely upon where we happen to be looking. By the final decades of the 20th century, astronomers had gathered an extraordinary collection of observations. Powerful radio galaxies stretched immense jets across space. Brilliant quasars shone from the edge of the observable universe. Some galaxies displayed unusually bright centres, but produced very little radio emission. Others appeared almost quiet, revealing only subtle hints of unusual activity. At first glance, these seemed like entirely different families of objects. Each received its own name, each appeared to tell a separate story. And for many years, scientists naturally assumed that nature had created many different kinds of cosmic engines. But astronomy has a wonderful habit of revealing simplicity where complexity once seemed unavoidable. Little by little, researchers began noticing something curious. Although these objects looked different from Earth, many of their hidden properties were remarkably alike. Their central black holes had similar characteristics. Their glowing accretion disks behaved in familiar ways. Their surrounding clouds of gas followed comparable patterns. Even the enormous dust torus that wrapped around the central region appeared again and again. It slowly became difficult to escape a simple question. What if these were not different engines at all? What if they were simply different views of the same remarkable machine? Imagine standing beside a lonely lighthouse on a rugged coastline. From directly in front, the brilliant beam shines into your eyes. Walk around to the opposite side and the lighthouse suddenly appears much dimmer because the tower itself blocks the light. Climb into a nearby boat and you begin seeing the beam sweep gracefully across the ocean. Fly high above in an aircraft and the entire structure takes on yet another appearance. The lighthouse never changed. Only your point of view did. Astronomers gradually realised that active galaxies behave in much the same way. This idea became known as the Unified Model of Active Galactic Nuclei. The name may sound formal, but its message is beautifully elegant. Many of the different active galaxies we observe are fundamentally the same kind of object. Their different appearances arise largely because we happen to observe them from different directions. The thick ring of dust surrounding the central engine plays an especially important role. If we are looking almost directly into the opening of that dusty ring, we can clearly see the brilliant accretion disk surrounding the black hole. The galaxy appears dazzling, energetic, and unmistakably active. If our line of sight passes through the dusty material instead, much of the brilliant light becomes hidden. The galaxy still contains the same central engine, but its appearance changes dramatically. It is a little like watching a theatre performance. Someone seated in the front row enjoys an unobstructed view of every actor. Another person sitting behind a tall column may hear every word but see only part of the stage. A third viewer watches from a balcony above, gaining a completely different perspective. The play remains exactly the same, only the audience's viewpoint has changed. This simple idea explains why Seyfert galaxies appear different from some quasars, even though both may contain actively feeding supermassive black holes. It also helps explain the striking appearance of radio galaxies, whose enormous jets become one of their most recognizable features. Then there are the objects known as blazars. Among the most dramatic sources in the universe, blazars seem capable of changing brightness with astonishing speed. Some become dramatically brighter over surprisingly short periods before fading once again. For many years, this rapid behaviour puzzled astronomers. Eventually, the answer turned out to be surprisingly geometric. Imagine someone standing far away in a dark field holding a powerful flashlight. If they sweep the beam across the landscape, observers standing to one side notice only a faint glow. But someone positioned directly in line with the beam suddenly experiences an intense burst of light. Nothing about the flashlight itself has changed. The difference lies entirely in the direction it points. A blazar is thought to be an active galaxy, whose powerful jet happens to be aimed almost directly toward Earth. Because the particles inside the jet are travelling extraordinarily close to the speed of light, their radiation becomes concentrated along the direction of motion. From our perspective, the jet appears exceptionally bright. Even small changes inside it become greatly amplified. This explains why blazars often seem so energetic and variable compared with other active galaxies. Not every active galaxy, however, launches spectacular radio jets. Many are surprisingly quiet at radio wavelengths. Astronomers refer to these as radio-quiet active galaxies. The name can be slightly misleading. They are not truly silent. Instead, they simply produce much weaker radio emission than their more dramatic cousins. Their central black holes continue feeding. Their accretion disks continue glowing. Yet for reasons that researchers are still exploring, their jets either remain weak or never fully develop. The universe, as always, enjoys subtle variation. Perhaps the most fascinating surprise of all arrived only within the past few decades. Some quasars appeared to change their identity. For years, astronomers believed that active galaxies evolved over millions of years. Human lifetimes seemed far too short to witness meaningful change. Then careful observations revealed something astonishing. A few quasars dramatically altered their appearance within only years or even months. Bright spectral features faded away. Previously hidden features emerged. Objects once classified one way suddenly resembled an entirely different category. These remarkable objects became known as changing-look quasars. Imagine watching the moon on a breezy evening. Thin clouds drift silently across its face. Sometimes the moon shines brilliantly. Moments later it appears soft and muted. The moon itself has not changed. The view has. In some changing-look quasars, drifting clouds of gas and dust may temporarily block our view. In others, the amount of gas falling toward the black hole appears to rise and fall, causing the entire accretion disk to brighten or dim. Whatever the precise explanation, these discoveries remind astronomers that active galaxies are not frozen monuments. They are living systems. They breathe, they fluctuate, they respond to changing supplies of fuel. Some brighten, some fade, some remain quiet for millions of years before awakening once more. The universe is not a static painting hanging upon a wall. It is a slow performance unfolding across unimaginable spans of time. As our understanding deepened, one final realization quietly emerged. Quasars are not merely fascinating because they are bright, nor because they launch immense jets. Their greatest significance lies in the influence they exert upon everything around them. The energy pouring outward from these active galactic hearts does not simply disappear into empty space. It reshapes entire galaxies. It determines where future stars may, or may not, be born. And in doing so, it may even help explain why galaxies like our own came to look the way they do today. When people first hear about quasars, it is natural to focus on their astonishing brightness. After all, an object capable of outshining an entire galaxy captures the imagination almost immediately. It feels like the ultimate display of cosmic power. But brightness alone is not what makes quasars so important. Their greatest influence comes from something much quieter. They change the future of the galaxies that surround them. For many years, astronomers imagined that galaxies and their central black holes lived almost independent lives. Galaxies formed stars while black holes quietly waited in their centres, occasionally consuming passing gas without greatly affecting the enormous systems around them. It seemed like a reasonable picture. The black hole occupied only a tiny region near the centre. The galaxy stretched across hundreds of thousands of light years. Surely something so small could not influence something so vast. Nature once again had a more interesting story to tell. As telescopes became more powerful, astronomers began measuring both the masses of supermassive black holes and the properties of the galaxies surrounding them. Gradually, an unexpected pattern appeared. Larger galaxies tended to contain larger black holes. Galaxies with more massive central bulges almost always possessed more massive black holes at their hearts. The relationship was surprisingly consistent across many different galaxies. It was almost as though both had grown together throughout cosmic history. Imagine visiting an old forest. The tallest trees usually have the widest trunks. Neither measurement causes the other directly, yet both tell the story of many decades of shared growth. The tree and its trunk mature together. Astronomers now believe something similar happens between galaxies and their central black holes. As one grows, the other often grows as well. This relationship became one of the strongest clues that galaxies and black holes are deeply connected. But how could such a tiny central region influence billions of stars spread across unimaginable distances? The answer lies in energy. When a quasar awakens, it does not simply produce light. It releases tremendous amounts of heat. It launches powerful winds. It sends enormous jets streaming far beyond the galaxy itself. Those outflows begin interacting with the surrounding gas, the very material from which future stars would otherwise be born. To understand why this matters, imagine a gardener caring for a large fruit tree. At first, pruning branches may seem destructive. Leaves fall, small branches disappear, the tree appears smaller. Yet careful pruning often helps the tree grow more healthily in the years ahead. By removing excess growth, sunlight reaches deeper branches, disease spreads less easily, and the tree uses its resources more efficiently. The gardener is not fighting the tree. The gardener is quietly shaping its future. A quasar performs something surprisingly similar on a galactic scale. Its energy can sweep enormous clouds of gas away from the central regions of a galaxy. At first glance, this might seem unfortunate. After all, gas is the raw material needed to build new stars. Yet if too much gas collapsed all at once, galaxies might consume their fuel surprisingly quickly, creating vast numbers of stars before exhausting the supply. Instead, quasar activity often acts as a regulator. It slows the process. It spreads the fuel over much longer periods. The galaxy breathes instead of burning all at once. Another comparison may help. Imagine heating a comfortable room with a fireplace. A small fire gently warms the space. If the flames become too large, the room quickly grows uncomfortable. Opening a window allows some heat to escape until balance returns. In many active galaxies, the black hole behaves almost like that window. As more gas falls inward, the central engine grows brighter. The resulting winds and radiation push some of the surrounding gas outward. With less fuel available, the black hole gradually quiets. The process naturally regulates itself. Astronomers refer to this as black hole feedback. Although the name sounds technical, the principle is wonderfully familiar. Actions produce consequences. Consequences restore balance. This feedback can take several different forms. Sometimes enormous streams of fast-moving gas race outward from the galactic centre, carrying away material that might otherwise have formed stars. Sometimes the powerful jets heat enormous reservoirs of gas surrounding the galaxy. Warm gas cools much more slowly, delaying the birth of future generations of stars. In other situations, the expanding outflows compress distant clouds, gently encouraging star formation in neighbouring regions instead. Nature rarely follows only one path. It adjusts to local circumstances with remarkable flexibility. These processes unfold across millions of years, far longer than any human civilization has existed. Yet today, astronomers can observe galaxies caught at many different stages of this long story. Some are actively feeding their central black holes. Others display enormous winds flowing outward. Some have already become quiet, preserving only faint memories of their energetic youth. Together they form something like a family album spanning the lifetime of galaxies themselves. Quasar activity also helps spread the products of earlier generations of stars. When massive stars reach the ends of their lives, they create many of the heavier elements that later become part of planets, oceans, mountains, and living creatures. Powerful galactic winds can carry some of these elements far beyond their original homes, gently enriching the vast spaces between galaxies. In time, some of that material may become incorporated into entirely new galaxies. The calcium in distant rocks, the iron inside future planets, the oxygen breathed by unknown forms of life. All may owe part of their long journey to ancient galactic outflows. Even our own Milky Way may carry subtle memories of such events. Although Sagittarius A Star is relatively quiet today, the enormous Fermi bubbles we encountered earlier suggest that our galaxy experienced a much more active period in the distant past. During that ancient episode, energy flowing outward from the central black hole may have influenced the movement of gas throughout the inner regions of the Milky Way. It may have slowed star formation in some places while encouraging it in others. It may have helped determine where future generations of stars eventually appeared. Perhaps even our own sun formed within a galaxy whose earlier history had already been gently shaped by one of these powerful episodes, not because the black hole created the sun directly, but because it quietly helped sculpt the galactic environment from which our solar system eventually emerged. It is a humbling thought. The peaceful night sky above us may carry traces of events that occurred millions of years before Earth itself existed. The stars we admire today are not isolated lights. They are part of an intricate conversation between gravity, gas, magnetic fields, and time. Yet despite everything astronomers have learned, one profound mystery remains. If quasars possess such extraordinary influence, how did the very first ones appear so astonishingly early in the universe's history? How did black holes grow from tiny beginnings into giants before the cosmos itself was even 1 billion years old? That question continues to challenge some of the brightest minds in modern astronomy. The farther astronomers looked into the universe, the more surprising the story became. For many years, scientists believed they understood the general life cycle of supermassive black holes. Small black holes formed first. They slowly gathered gas, occasionally merged with one another, and after billions of years eventually became the enormous giants capable of powering quasars. It was a comfortable picture. Patient, orderly, entirely reasonable. Then observations began revealing quasars that seemed far too old to fit that timeline. Or perhaps it is more accurate to say they were far too young. Some of the most distant quasars we have ever observed already existed when the universe itself was less than 1 billion years old. In cosmic terms, that is remarkably early. It is rather like finding an ancient oak tree standing proudly in a landscape that should have been covered only by newly sprouted grass. How could something so enormous appear so quickly? That simple question has become one of the most fascinating mysteries in modern astronomy. To appreciate the challenge, imagine planting a tiny seed in your garden. You return the following morning expecting to see nothing more than a small green shoot. Instead, you discover a towering tree reaching high above your house. Your first reaction would probably not be admiration. It would be confusion. Some important part of the story must be missing. Astronomers experienced something remarkably similar. The earliest quasars appeared to contain black, holes weighing hundreds of millions or even billions of times the mass of our Sun. Growing such giants through ordinary feeding alone seemed almost impossible within the available time. Nature appeared to have found a shortcut. The challenge was discovering what that shortcut might be. One possibility begins with the very first generation of stars. These ancient pioneers are known as population 3 stars. Unlike stars forming today, they were born in a universe that contained almost nothing except hydrogen and helium. Heavier elements such as carbon, oxygen, silicon and iron had not yet been forged inside earlier generations of stars because there had been no earlier generations. The first stars therefore grew under very different conditions. Many astronomers believe they became extraordinarily massive. Some may have lived only a few million years before collapsing under their own gravity. When they reached the ends of their brief lives, they may have left behind relatively large black holes. These newborn black holes could then begin feeding, merging, and gradually increasing their mass over time. It is an elegant idea. Yet even this process may still be too slow to explain the earliest known quasars. So researchers began imagining another possibility. Instead of forming a massive star first, perhaps an enormous cloud of gas collapsed directly into a black hole. Imagine watching snow gently accumulate across a hillside. Normally small snowballs appear first. Over time they roll downhill, collecting more snow and gradually becoming larger. But now imagine that an entire section of the hillside suddenly collapses together all at once, forming an enormous snowball from the very beginning. This is roughly the spirit behind the direct collapse model. Rather than building upward from a small beginning, nature might occasionally skip several intermediate steps and create a remarkably massive seed immediately. If such events occurred, they would provide black holes with a tremendous head start. Another piece of the puzzle may involve the way black holes feed. Earlier we explored the idea that brilliant radiation naturally pushes against falling gas, creating a gentle balance that limits growth. Yet observations suggest that some young black holes may briefly grow even faster than this balance would normally allow. During these episodes of super Eddington growth, the inward flow of gas somehow continues, despite the intense outward pressure from radiation. Exactly how this happens remains an active area of research. Some computer simulations suggest that thick flows of gas may trap part of the escaping light, reducing its ability to push material away. Others propose that gas may arrive in uneven streams rather than smooth, symmetrical layers, allowing some regions to continue feeding efficiently, while others are blown outward. Nature often proves more inventive than our simplest models. Mergers between galaxies almost certainly contribute as well. Throughout the young universe, galaxies lived much closer together than they do today. Encounters occurred frequently. Each merger delivered fresh supplies of gas toward the central regions. Sometimes two black holes also found themselves moving toward one another. Eventually they formed a gravitational partnership slowly spiraling closer together as they exchanged energy with surrounding stars. Yet even this elegant dance contains a mystery. When the pair becomes extremely close, their progress appears to slow dramatically. Astronomers call this the final parsec problem. In everyday language, the two black holes complete nearly their entire journey, only to hesitate during the final stretch before merging completely. Exactly how nature overcomes this apparent slowdown remains uncertain. Perhaps additional stars help carry energy away. Perhaps dense gas provides the missing assistance. Perhaps several processes work together. The universe has not yet revealed every detail. Some researchers search for another missing chapter entirely. Perhaps between ordinary stellar black holes and supermassive black holes exists an important middle generation. These objects, called intermediate mass black holes, would fill the enormous gap between the smallest and largest known black holes. Although several promising candidates have been discovered, astronomers continue searching for definitive evidence. Finding large numbers of these intermediate objects would help explain how cosmic giants gradually assembled themselves over time. Other ideas are even more adventurous. Some theories suggest that unusual concentrations of dark matter might have helped enormous gas clouds collapse more rapidly during the universe's earliest history. Others explore the possibility of primordial black holes, hypothetical objects that may have formed directly from unusually dense regions shortly after the Big Bang itself. If such primordial black holes exist, they could have provided remarkably early seeds for later growth. At present, however, no direct observational evidence has confirmed this possibility. Perhaps the greatest surprise has arrived in recent years. The James Webb Space Telescope has begun observing galaxies that existed astonishingly early in cosmic history. With each new discovery, astronomers gain another glimpse into an era that was previously hidden from view. Some observations fit comfortably within existing theories. Others quietly challenge them. Several newly discovered galaxies appear more mature than expected. Some early black holes appear surprisingly massive. Each observation acts like another piece of an unfinished puzzle. Sometimes the new piece fits perfectly. Sometimes it forces us to rethink the shape of the entire picture. This is one of the quiet joys of science. Every answer opens another question. Every discovery expands the horizon just a little farther. And perhaps nowhere is that spirit more beautifully illustrated than in our continuing search to understand the first quasars. They remind us that the universe still keeps many of its oldest memories hidden behind veils of time, patiently waiting for curious minds and ever more capable telescopes to uncover them. As our journey begins to draw gently toward its close, it is comforting to return home. For much of the night we have travelled across billions of light years, visited galaxies from the dawn of cosmic history, and stood beside some of the brightest objects the universe has ever created. Now, let us quietly return to our own galaxy. The Milky Way appears calm today. Its spiral arms continue their graceful rotation. New stars are still born inside cold clouds of gas. Older stars slowly orbit the galactic centre, each following a path shaped by gravity over millions of years. Sagittarius A Star rests quietly at the heart of it all. If someone from another galaxy happened to observe the Milky Way today, they would probably not describe it as extraordinary. They would see an ordinary spiral galaxy living through a peaceful chapter of its long existence. But galaxies, like forests, oceans and mountains, are never truly still. They change, not quickly, not dramatically from one human generation to the next, but steadily, patiently, over spans of time almost beyond imagination. Far beyond any future that humanity is likely to witness directly, another great spiral galaxy continues drifting toward us. This is the Andromeda Galaxy. Although it lies more than 2 million light-years away, gravity has been quietly drawing our two galaxies together for billions of years. Imagine two broad rivers flowing through a wide valley. From a distance, they seem entirely separate. Year after year, they gently bend toward one another until, almost without anyone noticing, they finally meet and become one larger river. The future meeting of the Milky Way and Andromeda will unfold with similar patience. It will not resemble the sudden collision of two solid objects. The stars themselves are so widely separated that very few, if any, are expected to collide directly. Instead, gravity will slowly reshape both galaxies. Their elegant spiral arms will stretch and twist. Immense clouds of gas will drift inward. Entire populations of stars will find themselves following new orbits. The dance may continue for hundreds of millions of years before finally settling into a new, larger galaxy. For the black holes waiting at the centres of both galaxies, this meeting may provide something they have not enjoyed for a very long time: fresh fuel. As enormous clouds of gas lose energy during the merger, much of that material is expected to flow toward the galactic centres. Some will begin spiralling around Sagittarius A Star. Some will feed the supermassive black hole now resting inside Andromeda. Eventually, those two ancient giants themselves may begin an even slower dance around one another. Separated at first by thousands of light years, they will gradually move closer as gravity exchanges energy with surrounding stars and gas. After an unimaginably long journey, they are expected to merge into a single, even larger black hole. Long before that final embrace, however, something remarkable may happen. Both black holes could awaken. Just as we explored earlier, fresh supplies of gas would allow glowing accretion disks to form once again. The quiet galactic centres could become brilliant active nuclei. Jets might reappear. Powerful winds could once again shape the surrounding galaxy. For a time, the peaceful Milky Way we know today might resemble the distant quasars that first inspired this journey. It is a curious thought. The spectacular objects we observe across the distant universe may not be strangers after all. They may simply represent another chapter in the life story of galaxies much like our own. In that sense, quasars are not rare cosmic accidents. They may instead be natural phases through which many large galaxies pass as they grow, merge, and evolve. The universe is filled not only with places but with stories. Each galaxy has its own beginning, its own seasons, its own quiet years, its own moments of astonishing brilliance. Even after centuries of careful observation, astronomers know that many questions remain unanswered. Exactly how the first supermassive black holes formed, why some galaxies launch powerful jets while others remain comparatively quiet, how magnetic fields organise themselves so efficiently, whether hidden populations of intermediate mass black holes are still waiting to be discovered, how many ancient quasars remain beyond the reach of today's telescopes. Each generation of scientists inherits these questions from the one before. Each generation also builds better tools. The James Webb Space Telescope has already transformed our understanding of the early universe. Future observatories promise to reveal even more. New radio telescope arrays will map enormous regions of the sky with unprecedented sensitivity. Future space telescopes may observe galaxies from even earlier moments in cosmic history. Gravitational wave observatories operating in space may one day detect the gentle ripples produced when supermassive black holes slowly spiral together before merging. Instead of observing only light, humanity will increasingly learn to listen to the quiet rhythms of gravity itself. Every new instrument extends another sense. Every new discovery gently reminds us that nature is usually more imaginative than our expectations. Perhaps that is the deepest lesson quasars offer. When Carl Yansky first noticed a faint radio whisper arriving from deep space, he could not have imagined that the path would eventually lead to supermassive black holes, magnetic fields stretching across galaxies, and some of the brightest objects in the observable universe. One unexpected observation became another. One mystery opened the door to countless others. Science often advances in exactly this quiet way. not through certainty, but through curiosity, not by believing we already understand everything, but by remaining willing to ask one more gentle question. And perhaps there is something deeply comforting about that. The universe does not ask us to solve all of its mysteries tonight. It simply invites us to keep looking, to remain curious, to appreciate that even after centuries of exploration, the night sky still contains wonders beyond anything our ancestors could have imagined. As you rest beneath that same sky, it is pleasant to remember that somewhere beyond the countless stars, ancient quasars continue shining across the darkness. Their light began its journey billions of years before our world existed. Tonight, a tiny fraction of that ancient light reaches us at last. It reminds us that the universe is both vast and patient, complex and beautifully simple, filled with mysteries, yet generous enough to reveal them little by little to those who quietly wonder. And perhaps, as your thoughts become lighter and the night grows still, you can simply imagine those distant beacons continuing their silent journey across the cosmos, while our own quiet galaxy waits peacefully for the distant chapters that time has not yet written. For now, the Milky Way rests. So, perhaps, can you? Good night.